most people, the expression unidentified flying object brings to mind images of interplanetary spacecraft. However, the theory that aliens exist has met with many objections. Some scientists will even say that it's nothing more than nonsense. According to them, if we consider the vast distances that separate the stars, it is ridiculous to think that aliens could be visiting us. For instance, if we look at the star that is closest to our sun, Alpha Centauri, we see that it is slightly more than 4 light years away from Earth. In other words, it is as far as light would travel in 4 years. Since light travels at a speed of 300,000 kilometers per second, we're talking about a distance of approximately 38 billion kilometers. That would be the number 38, followed by 12 zeros. Even if we could imagine an alien civilization capable of traveling at close to the speed of light, they would take at least 4 years to get to our planet and another 4 to get back home. And if they decided to trade in their spaceship for a car driving down the highway at 60 miles per hour, our intergalactic travelers would take 120 million years to cross the same distance. And to do what? To butcher a few cows in the U.S. Midwest? To kidnap a Boston postal worker? To gather a few samples of lavender in France? Let's get serious. We now know, based on certain criteria, that Alpha Centauri cannot have any habitable planets orbiting it. This means that if aliens do exist and are visiting our planet, they must have come from somewhere else, somewhere much farther away. But where could that be? We might be getting off track. It might not be as far away as we think. The speed of light might not be as absolute as astrophysicists claim, and somewhere else may turn out to be nowhere. The universe has by no means revealed all of its secrets. The UFO problem raises 2 questions with regards to aliens. First of all, do intelligent life forms exist in the universe? Secondly, do they have the means to visit us? In terms of biochemistry, life as we know it is like a cake recipe. Certain ingredients are required. Professor René Racine is considered by many as one of Quebec's leading astronomers.
I'm no expert, but they think that life is carbon-based, and only a mixture of elements such as carbon, nitrogen, oxygen, and hydrogen could produce life, or the level of molecular complexity necessary to generate life forms. Other combinations also exist. For instance, silicon mixed with oxygen gives sand, but it's far from being as malleable and fertile as, say, blood, for example, which is composed of carbon, nitrogen, and oxygen. Carbon, nitrogen, oxygen, and hydrogen exist everywhere in the universe. So all we need is the right conditions for these elements to combine, then increase in complexity and evolve into a life form.
Obviously, simply mixing elements such as hydrogen, oxygen, and carbon together is not enough to spark the complex process that produces life. Going back to our cake recipe, tossing a couple of eggs, some flour, and sugar into a bowl and mixing them together doesn't give us a cake. The mixture needs to spend a certain amount of time cooking in the oven at a specific temperature. In cosmic terms, the equivalent of the cooking process for this hydrogen, oxygen, and carbon mixture is referred to as planetary conditions.
We need to understand that the conditions required to create this biological or living soup are very precise. There's the time element, the stability of the planet's orbit, and surface temperatures. And it's hard to find ideal conditions where all of these elements coexist. We've known that for a long time. It makes us realize how incredibly unlikely it was for life, especially intelligent life, to emerge here on Earth. And yet, it happened. To be more precise, It's believed that a planet's surface temperatures must allow for biochemical reactions to take place. Therefore, they must remain within a certain range. They have to stay between water's freezing point and evaporation point, for example, since water is an essential element. And the orbit of the planet, or the object on which a life form might develop, must be very constant. Planets orbit around stars, just like Earth orbits around the Sun. And if the distance between the planet and its star varies over time, surface temperatures will change. Now you can see why we are so concerned with the effects of an increase in temperature on Earth's ecosystem. Even a change of 1 or 2 degrees can have a catastrophic result. To keep the temperature constant, it's crucial that Earth's orbit remain as circular as possible. Earth is always the same distance from the Sun within a 1% margin. That's just one example among several others. From our observations, we now know that when planets or other protoplanetary objects form around young stars, there is a dynamic of intense agitation. And it's not easy to explain how a solar system such as ours could have come about, in which there are 8 or 9 planets, if we include Pluto, whose orbits are nearly perfectly circular. So those are the conditions. And I've given you an idea of how difficult it is for all of those conditions to be present at once. It happened here in our solar system. There was a planet called Earth, just the right distance away from its star for the water to maintain its fertile properties. Water can be too hot or too cold. The temperature of Earth's water may not have been ideal at first. The Sun may have been hotter in the beginning. Mars might have had a relatively high surface temperature. There may have been arch biology on Mars. Who knows? The point is, it's very difficult to meet all of the conditions at once.
In the early 1960s, scientists were optimistic about the existence of extraterrestrial life forms. They used planetary conditions found here in our solar system as a model, believing that the same model must exist everywhere else in the universe. But recent discoveries of planets outside of our solar system have put a damper on their optimism. It seems that stable planetary systems are actually a lot rarer than we had thought up until now.
Establishing our level of knowledge or confidence is a question of statistics. In the 1960s and 70s, Frank Drake came up with a relatively simple mathematical equation that included the probabilities of each factor required for life to emerge. What is the probability that a star will have planets? What is the probability that these planets will have a stable orbit? What is the probability that the planet will be far enough away from the star? If we want to calculate the probability of communicating with extraterrestrial life forms, what is the lifespan of a civilization capable of communication? I recall at the time, we would multiply all of these factors by the number of stars in the galaxy, and the answer would be a few units. There would only be a few habitable planets where life could develop in our galaxy, the Milky Way. But back then, we were going on the supposition that all stars have planets. And now we know that's not true. There has been a lot of talk about discoveries of planets outside of our solar system. But we have to remember that the 80 or so planets that have been discovered so far were among 3,000 stars that were examined. This shows that it's not 100% certain that a star will have a planet. In reality, the probability is more like 2 or 3%. What's even worse, if we include in our probabilities the total number of planets discovered around stars, there are planets whose orbit is irregular, or elliptical, or whose surface temperature varies between 100 and 300 degrees Celsius, not over a period of millions of years, but over a period of weeks or days. I would say that recently, over the past 5 years or so, the consensus has been that the creation of life as it occurred here on Earth happens very rarely elsewhere.
Produite très rarement à l'extérieur.
L'optimisme de Drake, au début, eh bien, était basé sur...
Drake's initial optimism was based on the fact that there are over 10 billion stars in our galaxy.
d'étoiles. Alors, à ce moment-là, bien, les chances qu'on en trouve quelques-unes...
At the time, it was believed that chances were pretty good of finding stars with planets orbiting around them.
Les planètes qui tournent autour de ces étoiles-là, eh bien, pourraient quand même être significatives. Mais
We have since discovered a lot of massive planets.
beaucoup de planètes massives.
But according to the basic criteria, these massive planets could not have formed close to their star.
Massives-là, bon, bien, ne peuvent pas être formées près de leur étoile.
They would have had to form far away from the star, like Jupiter did in our solar system. Jupiter is 5 times further away from the Sun than the Earth is. So these massive planets must have moved closer to their star over time. At first, we wondered how that could happen. But after much study, we realized that it was relatively easy for a planet as big as Jupiter to evolve and then migrate from the position where it was formed to a new position closer to the star. Which makes us wonder, if this is possible, then why is Earth still in the same place where it is now? If Jupiter had moved closer to its star, like the other massive planets that we observed, then Earth wouldn't be here anymore.
De leur étoile, alors bien, la Terre ne serait plus là.
Now we're asking ourselves the question, why are we still here?
On pose plutôt la question inverse. Pourquoi est-ce que nous sommes ici? Et puis il semble que Jupiter serait un cas...
It seems that Jupiter is different from a lot of the planets that we discovered outside of our solar system.
Beaucoup des autres planètes extrasolaires.
The good news is that once all of the conditions have been met, it's easy for life to spring forth. In 1953, Stanley Miller, a young biochemistry student, took a sphere and filled it with the gases that were present on Earth 1 billion years ago. He then bombarded the sphere with strong electrical charges, recreating Earth's original climatic conditions. At the end of the experiment, Miller observed that his mixture had become enriched with an additional substance: amino acids, the building blocks of life. Miller's experiment proved that it was possible to create life from inorganic matter. As for the transition from organic life to intelligent life, it was just a question of time and ability. To help you understand this long process, let's imagine the Earth's entire evolution reduced to the length of a 24-hour day. If we start with the formation of the planet Earth at 12 a.m., then life does not appear until 5 a.m. The planet takes all day to develop, and the first mollusks do not appear until 8 p.m. Dinosaurs don't show up until 11 p.m. Then our human ancestors appear on the scene at 11:55 p.m. On this scale, the Industrial Revolution was a mere hundredth of a second, and space exploration has only been taking place for 3/1000ths of a second. If we try to imagine this long process taking place on another planet, it is almost certain that the original life form will eventually evolve into an intelligent species. However, it is highly unlikely that it would lead to humanoid beings. Unlikely, but not impossible. Michio Kaku is a professor of theoretical physics at the University of New York.
Exobiologists, that is, biologists that look for perhaps intelligent life forms on other planets, say that there are really 3 ingredients for intelligence, just 3. First is the ability to have some kind of language, culture, to be able to hand down communication from generation to generation. Second is a hand of some sort, a way to grab a tentacle, perhaps a claw, fingers, to manipulate the environment. And the third, eyeballs of some sort, some way to sense the environment. But that's it. Eyesight of some sort of grappling instrument, and some sort of culture, communication, language. Beyond that, anything goes. Look at the animal kingdom on the planet Earth. There are many animals that could, given a few million years, probably become intelligent. Octopus, for example, they have tentacles. Lobsters have claws. Mammals, if they had opposable thumbs, they would be able to manipulate the environment. Just on the planet Earth, we have a fantastic variety of animals without 2 eyes, nose, mouth, ears, chin, forehead in the exact proportion of a human. Therefore, when I see a picture of an alien that looks just like us, I tend to think that these are simply memories of 1950s science fiction movies when we saw bug-eyed monsters. Even on the planet Earth, the diversity of life forms is fantastic compared to what we see in science fiction movies. I would be more convinced if I saw an intelligent octopus or intelligent lobster. I would really be quite impressed if somebody says they were abducted by an intelligent octopus.
If anatomical shapes are infinite, then what about intelligence levels? Can you imagine what an extraterrestrial civilization 1,000 or 10,000 years ahead of us might be like?
We physicists believe that when you look in outer space, we have type 1, type 2, and type 3 civilizations. A type 1 civilization is perhaps 100, 200 years more advanced than ours. They control planetary energy, anything involved with the planet, the weather, perhaps earthquake and volcanoes, they can control. However, eventually, they expand by a factor of 10 billion to have the power of a star. They control solar flares, a type 2 civilization. A type 2 civilization can roam across parts of the galaxy. They have the power of thermonuclear fusion, the power of stars themselves. Eventually, they exhaust the power of a star and they become galactic. They become type 3. They have tremendous accesses to huge, vast regions of our galaxy. A type 2 civilization is 10 billion times more powerful than type 1. A type 3 is 10 billion times more powerful than type 2. But on this scale, what are we? We are type 0. We get our energy from dead plants. We can only speculate what it would be to be like a planetary civilization, to be able to energize volcanoes and earthquakes and change the weather at will.
If such civilizations exist in the universe, what do these beings look like? And how can we detect their presence? In the early 1960s, anxious to obtain an answer to this question, scientists set up an ambitious project designed to listen to space. It was called Project SETI, Search for Extraterrestrial Intelligence. The idea was to use radio telescopes to listen in on the interstellar void in the hopes of picking up a radio signal of alien origin. Here on Earth, we use radio waves in practically all forms of communication. If extraterrestrials were living on a planet orbiting the star Zeta Reticuli, some 30 light years away from Earth, and doing the same experiment, they would just now be picking up old episodes of Hawaii Five-0 or The Invaders. SETI researchers had to choose a specific wavelength to listen in on. For convenience sake, astrophysicists decided to choose a wavelength that was equivalent or close to that of hydrogen, the most common element in the universe. So they chose 1420 megahertz. Since then, space has been hopelessly silent. Apart from a few abnormalities, like the signal picked up on August 15, 1977, which was dubbed the WOW signal, Project SETI has not recorded any signals that could be indisputably interpreted as a message from alien intelligence.